Yeah, thanks for this great introduction. While we're switching computers, a couple of words about myself from myself. I'm based in Barcelona, and currently I work in the company that is doing mobile decentralized apps browser for the Ethereum blockchain. Don't edit my slides, please.
I'm not.
All right, 1 second. All right, but most of my experience comes from server-side backend development. I was working for 8 years in security, in home security market. So the topic I'm going to talk about today is something that resonates very deeply with me, and I've seen a lot that people in teams misunderstand this, and it causes problems. I also aware about this title, you know, it's a bit clickbaity, like every developer should be. You could say this pretty much about anything. Good writer, good communicator, good psychologist, right? But yeah, it's still good enough, you know. Sometimes it's challenging to find a good title. So let's start. The recent study from the Massachusetts Institute of Technology has found a staggering 87% chance that Linus Torvalds actually hates your code. It's obviously a joke. The real number is much higher. But one of the possible reasons why it's probably true is that Linus Torvalds is a huge proponent of the idea designing the code around the data and not vice versa. One of his famous quotes says, "Bad programmers worry about the code, and good programmers worry about the data structures and relationships between them." But there is nothing new in this phrase. It's been known for the decades in computer science, and there is another quote from the Fred Brooks: "Show me your code and conceal your data structures, and I shall continue to be mystified. And show me your data structures, and I won't need your code. It'll be obvious." So designing the programs around the data is something that we learn actually at the start of computer science courses. It's in the textbooks. We learn these big O notations of complexities of data structures and algorithms. That's why we actually have different data structures to choose the proper one for the proper type of data we work with. So this concept is well known. I won't stop here too much. But talking about data structures, raise your hand if you have designed your own non-standard data structure recently. Not data type, but data structure with new properties. Okay, a couple of hands. Raise your hand if you implemented your own custom algorithm, something from the paper or, all right. And raise your hand if you have written the microservice or service in like last year. Yeah, this is it. Our programs now are distributed systems, and our hardware is a cloud. We could visualize it in the following way. So at the beginning, programs didn't have functions. Back in the 50s, there was just algorithm with just one input and one output. And that was it. Later, we got higher level programming languages, and we got notion of function. I think it first appeared in second version of Fortran. So it allows us to call different algorithms and combine the output from one algorithm to the input of another and combine them in different ways, so we could process more complicated inputs and produce more complicated outputs. And now we're going to another scale of this. Our distributed systems is essentially the same, but at a different scale. The system consisting is from different services and microservices usually, just calls your services the same way how your normal program calls the function. It's just a different zoom level. So you may think about RPC calls as a calling the function locally, right? But on the different scale. Just replace function with RPC and you have the same abstractions. Another way to think about it is compare inlining functions versus calling external functions and calling local code versus calling remote node, right? You know, in compiled language, we usually have this thing called inlining. So if calling function is too expensive, it's usually better to call it, to inline it into the stack. But currently, calling function externally, which is like normal function call, is so cheap that we don't even think that it's expensive, right? We don't do inlining anymore manually, in very, very rare cases. But calling RPC call via network is still expensive. But you know, it's hard to predict the future. We might be much closer to reliable, extra reliable, and extra fast networking. Maybe it's much closer than we think. So think about what will happen if calling function over the network will be as cheap as calling function locally. Like, you don't use sorting microservice, right, to sort the data usually, but imagine that it's the same cost of calling this function. What will happen then? And if you think this is crazy idea now, the company called Algorithmia already doing that. They have thousands of algorithms on their website, starting from the very simple ones, like date conversion, to latest models for computer vision and deep learning. And they got recently 10 million investments from Google. And you use them actually literally like that. You specify ID of the algorithm, you provide the input, and you read the output, and that's it. And obviously, that could be done in one line. So back to the concept of designing programs around the data. The point I'm trying to make here is that this same concept could be applied to designing algorithms and designing systems, the whole systems. I want you to shift your perspective and think about distributed systems as a one big programs. But it sounds a little bit abstract probably right now. So a few examples, real-world examples of real companies that were gaining a lot of benefits of designing or redesigning their systems based on the data they work with. And the first example is the Twitter story, how Twitter refactored their media storage system. You know how Twitter works? Twitter is just a bunch of users sending short text messages and reading them back. They also can upload images and videos. Sort of simple thing, right? Most of the problems they have due to scale, they have enormous scale, probably a few billions people using them. And for the media, I mean images and videos, they have to handle user upload. They have to resize the images or video for different screen sizes, for the retina, for different phones, store this, and return when user requests the image. Kind of simple, right? But they had a lot of problems with the uploading part. And so they scheduled the huge refactoring of this subsystem. And one of the particular problems they had is the huge amount of data they were using. It was about 6 terabytes per day. And it only were going to grow, obviously. So as a part of this refactoring, they did data research. They asked, let's look at the data we work with. Maybe we will be able to find some patterns that we could exploit and then take some interesting trade-offs based on this. Maybe we can gain something. And they did. They found actually interesting thing. Half of the requested images were at most 2 weeks old. And after 20 days, probability of image or video to be requested was negligibly low. And I mean, this is logical, right? This is how we use Twitter. We usually go to Twitter to check the latest tweets, not to check what was a month ago or a year ago. So what they did, they created a new server that allows you to resize image on the fly. This is obviously much slower than serving already pre-resized images, but it was good space-time trade-off. They kept image variants for 20 days, and after that, they delete them and just resize on the fly. That was very smart space-time trade-off. What they achieved with that? Their storage usage dropped almost by 4 terabytes per day. They used twice as less as computing power, and they saved companies $6 million just for 1 year. I think it's a pretty fascinating example. They just looked at the data. They could solve it in a traditional way. They just throw more money and more servers, right? Another example is from one of my former employers. It's rather an anti-pattern how not to use it. So similar to Twitter, they had a lot of data, users that send data and read them, and this data need to be filtered and searched. So users were going to their account and search something. And this particular operation of search became really, really slow as data grew. It's not even slow. There were database outages, sometimes for 2-3 days. And yeah, you heard it right. It's like 2 days that database was slow at the point that it almost stopped. This is sort of outages that can kill the company. So our team made a huge data research. And actually, it was inspired also by Twitter's story. And we found a similar pattern, which seems to be a kind of human-related thing. After 2 weeks, most of the data was dead weight. This was interesting. But also we found that most of the data was isolated. Unlike typical projects, there was no cross-linking between data. We could exploit it. And most of the data was really, really small. Something that, everyone dreamed to work with. And by small, I mean 90% of data was less than 10 by 10 two-dimensional table of strings, and most of the strings were actually empty or small. That allows us to use so-called property of the small numbers. When n is small, everything is fast. Naive slow algorithms could be much faster than sophisticated algorithms because complexity, this ON complexity for the algorithms usually is calculated for the large n. We can visualize it in the following way. And obviously we could use data retention approaches similar to the Twitter. A lot of trade-offs could be exploited there. But the company decided to solve this problem by switching to another database. The logic of the manager was, the switch was from MySQL to Elasticsearch, and the logic of the manager was, we have a problem with database on search, so let's switch to another database that has search in its name. So when you ignore the data, it's not the software engineering anymore. And I think the root cause of this was that team and manager specifically didn't see the whole system as a program that should be designed around the data. Another example is the Revelant story. Revelant is a company, London-based company. They're doing fraud detection for financial market. It works like a service. So clients, usually processing systems, make an API call to them with a bunch of data for the payment, and they ask, hey, can you quickly say, is it fraud or not? To accomplish that, they obviously use machine learning, and for machine learning, they need to train their models, and these models are trained on so-called features. And features usually something simple, like rate of dates, rate of cards added, orders, etc. Some exotic things, like distance on keyboard between the letters in the name. So if user is QWERTY, it's probably a fake user. But some data was more complicated. In particular, they need to connect things like emails, phones, devices, and other information, and check if any of this connection actually link to existing fraudsters, for known fraudsters. So they studied the problem offline, and they quickly realized that they were working with a graph, and so they needed a graph database. There is a whole market for these tools, for these databases, and they played with major players on this market, which is Neo4j, I think, the main one, Kaylee, which is written by Google, and Titan. They played with them and weren't quite happy. Some of them had maturity problems, some of them were just complicated. It's like completely new tool, new API, new set of vulnerabilities, maintainability, complexity, whatever. So I think that was just engineering, gut feeling that this is overcomplicated solution. they returned to the drawing board and asked one question: what data do we actually need? And it turned out that they were carrying only about one number of people that connected to you, and one Boolean value, whether any of those people are fraudsters or not. And based on that, they found a solution using just one data structure called union find, or disjoint set data structure. It's sort of exotic data structure. You don't use it like daily. But essentially, what it does, it allows you to very, very quickly determine if two items in one set, find an item and set it belongs to, and merge two sets. For example, you know that, hey, those people from those sets are connected, so let's merge this set. It allows you to quickly respond to questions like that. Like, does item 2 belong to the same set as item 7? Or what set item 3 is in? Or connect sets with 9 and 7, something like that. And one of the best properties of this data structure is it doesn't preserve the whole graph information. They actually didn't need it. It preserves only information they really care. So it has very low memory footprint, and it's crazy fast. There is a link with visualization, interactive visualization, really, really fancy. Check it out when slides are online. And the code, this is a real code from the original talk, from Revelant. Obviously, that's not the whole code, right? But you get the idea. This is code that you can understand and you can change. It's probably 2 or 3 orders of magnitude less code than Neo4j or other databases. And they achieved quite good results. Most of the responses were under 2 milliseconds, and average was 1 millisecond. They were super happy with the solution, and low memory footprint allowed them to shard clients per servers very efficiently, so they were really happy. And you know, less code means less bugs, less maintenance, less security problems. Code, what is important? Code fully owned by the team, and it's much easier to refactor and grow this code. So, what's the main outline? What's the main takeaway from this example? The systems designed around the data usually much simpler than you think. All right, I hope you convinced you that you should see the whole system as a programs and design them, apply the same principles that you apply to the programs. But is it enough just to look at the data? Are we able just to look at the data and ask the right questions? And I'm pretty sure that not. There was no evolutionary incentive to develop these skills in us. We are much better to conform the growth behavior rather than logically and rationally analyze the complex data sets, right? We have a lot of logical fallacies and cognitive biases, and we actually very, very terrible at statistical data analysis. We can't even grasp probabilities right. For example, what's the typical requests distribution? Let's say you write a server, a high-loaded server, and you're doing load testing tool. You want to simulate the real load. Most of the load testing tool is doing it like that. You ask me, give me 1,000 requests per second, and they start sending these requests in like each millisecond. Some doing better, they introduce random delay between calls, between requests, doing uniform distribution. But actually, there is one of the probably well-known, one of the best-known random distribution processes called Poisson process. And it looks like this. The Poisson distribution is distribution of any event that happened independently. So requests tend to come in batches, then had gaps, they had gaps, and then again the batches. This is actually very, very close to the real distribution of requests. And it make make the difference, for example, in case if you have a data race in your server, which is only could be detected during the, I don't know, some specific set of requests of some type going in the group. So, just an example. Another example, what's the probability of two people in this room having the same birthday on the same day? We usually start to think like, okay, this is 356 days in a year, and here probably 50 people, so okay, maybe 7%, right? But actually, it's very well-known birthday paradox, and the probability for the 50 people is 97%. And only for 23 people, it's 50%. But those examples probably just toy examples, not convincing you enough. And here's the story that involves real people lives because of misunderstanding of the data. This is a story about United States Air Force and averages. You might have heard this story. It was in articles, in a podcast, it was in a book. But here is the gist. In 1940s, United States Air Force had a serious problem. There were a lot of planes crashing. Even in non-war period, they were losing planes just like because of nobody knew why. Sometimes up to 17 crashes per day. And pilots just knew that, hey, that was just dangerous to fly. And usually it was happening on the landing or takeoff. They were blaming pilots, training programs. They were blaming planes itself, mechanics and electricity circuits. But investigation revealed that that was okay. So if it's not a plane and not a pilot, what else? And they turned their attention to the cabin. It's something in between the pilot and the plane, right? So the cabin at the time was designed in 1920 by the measurement of the pilots at the time, and it was suited for the average pilot. And so they thought, maybe, you know, just maybe from the 1920, pilots changed. Maybe they got bigger or smaller. There were no McDonald's at the time, but anyway. So they conducted a new research. They analyzed 4,000 pilots. They measured 140 different dimensions of their bodies, like length of the limbs, circumference of the chest, distance between the eyes, whatever, everything. And they checked how many pilots actually fit into the average. The question was, what percentage of pilots actually fits into this average model by 10 parameters relevant to the cabin design? Unless you know the story, try to guess what percentage of people. What's your intuition say? 80? 5%. 65? Okay, 0. It's not even 0%, it's like 0 people, nobody. There was no such thing as an average pilot. And only by 3 metrics, just 3.5% were in this range. And by the way, by average, they actually meant median plus minus 30%. So it's quite a big range, right? So United States Air Force ordered to make cabin adjustable, something that we take for granted now in cars. But at that time, it was like huge engineering shift in the mindset. And yeah, unexplained mishaps plummeted. So this story was told in a book called End of Average. And the author, actually, of this book doesn't explain why. Why did it happen? He just makes a statement that, hey, there is no such thing as an average human, and that's it. But explanation is actually more fascinating. An explanation is that we live in a 3-dimensional world, and most of our communication happens in 2 dimensions, but our intuition about the data mostly built on 1 dimension. And specifically for the averages. We tend to think that average is like where the most of the values are, but it's only a case for particular case of normal or similar distribution in 1 dimension. So average is more like a center of the mass. For example, average point of the donut is the whole. There is no values there. And for higher dimensions, actually things got really messy. This is how our intuition on average is formed. This is bell curve, we all know it, and like, yeah, we clearly see that most of the values are inside this range. What could go wrong? But when we go to the 2 dimensions, the ratio of number of the points of the values that lays outside this range and inside starts to shift towards outside. And 2 dimensions means that we have 2 metrics, for example, length of the arm and length of the leg. For the 3 dimensions, it gets even worse. More values go to the outside, to the periphery. And when we go further in number of dimensions, 4, 5, and up, most of the values actually go outside. As some professors say, n-dimensional orange is all skin. And this is super counterintuitive. Unless you study in n-dimensional spaces, there is no way you can figure it out just by, thinking process. It's something that you should be aware of. Yeah, and all our intuition is based in 1 and 3 dimensions. We can't think in higher dimensions. And usually, right, we think as higher dimensions is some, mumbo-jumbo, high math, physics topic. That doesn't have anything to us, but this is a story, real story, where people were dying. If engineers, United States Air Force engineers, were aware of these properties of one-dimensional spaces, that could save a lot of people's lives, right? So the point is, for many cases, we need math, we need statistics, we need to improve our intuition, and that's what we actually call data science. Data science is an interdisciplinary field. It combines math, statistics, probability theory, algebra, machine learning, visualization, computer science. It's really an intersection of many, many different fields. And probably my major point of this talk, that if you want to be a good software engineer, you should be passionate about the data science. And I specifically use this word passionate because everyone can't be, statisticians and mathematicians and machine learning experts, right? These are complex topics, but at least you have to know the basics. And this notion of passionate when you're passionate, you just you stumble upon some video on YouTube and hey, I'm interested in it, let's watch. Or you see the person who is skilled on this, you will ask her or him, and that's how we actually learn in real world. And yeah, so here's the point: you don't have to be a statistician, but you have to get the basics so you can ask the right questions. For example, in our case, from my former employer, I didn't do most of the research myself, but I went to the data team and I said, hey, I want you to look at this data, and we suspect that there might be some patterns. And after all, learning data science will improve your understanding of more complicated processes like politics, war, epidemics, like everything. And it will boost your intellectual curiosity. Where to start? I would say whatever works best for you. Some people prefer videos. Some people hate videos and they like textbooks, articles, whatever, meetups and classes. Yeah, and you can marry a data scientist. It's like no way you will be ignored by data science. Yeah, for example, here's the topics that I think most important that you should start with, unless you already know them. It's the basic statistics, probabilities, regressions, distributions, tools for exploring and working with this. It's mainly the R programming language. They have super cool R Studio, and the Python Pandas and Go GNOME. And basics would be nice to have at least basic understanding of neural networks, deep learning, and linear algebra. Speaking about videos, I can recommend, obviously, Coursera. Just go there and search data science. Sites as Udemy, I mean, you name it. There are nowadays a bunch of them. There is a fascinating project, Khan Academy. It's sponsored by Bill Gates and Melinda Foundation. It's really good. They use actually YouTube as a drawing board. It's like you sit in and see in person drawing on a board, explaining in the old school way. And it's all free. And there are many educational YouTube channels. Don't underestimate it. One of the channels in particular I want to promote, and I'm just praying on this, 3 blue, 1 brown. I don't know how this is one guy actually. I don't know how he's doing so awesome animations, but it's like crazy quality. I never saw anything like of this quality. And actually the last video from last week is explaining the neural networks. It's the best explanation I've ever seen. Speaking about meetups, there is a worldwide community called Papers We Love. You know, many computer science things and algorithms starts as an academic paper, and they usually read in the academic language, which normal people don't read. And this community is dedicated for people who loves reading them and explaining them in human language to other people. We start in this chapter of Papers We Love in Barcelona this month, and I hope someday, hopefully soon, there will be a chapter in Lviv or Kiev or other Ukrainian cities. Right, so my main takeaways from this talk is first, start to think about distributed systems as a one program and apply the same concepts. Second, always ask the question about the data. And to ask the right question and to make sense of this data, learn data science, be passionate about it. Some links used in this presentation, and I think that's it. Yeah, thank you.